three-dimensional marine spatial analysis of abiotic covariates.
Hello, and thank you for having me. Today I want to talk about a R package that I've developed, sharkabc3d. So we'll be looking through a number of different projects that motivated this package's development to sort of tell the story of how this came to be. And so in a recent paper, I created these maps to show where in the world held the greatest diversity and concentration of sharks and rays. And so we're used to seeing species richness maps like this map that I made here, a 2D representation of our oceans. This is made by taking a species range, overlapping them with grid cells. Nice and simple. The problem. Sharks, rays, and chimeras occupy almost every marine environment, from the surface to over 3,000 meters in depth. But often analyses for this clade are done in 2D, even when species live in completely different slices of the water column. The environmental variables of the sea surface versus the seafloor are going to be different. A long line scraping or a long line hooking at 80 meters and a bottom trawl scraping the sea floor at 400 meters all occur in the same cell in 2D. And so my first 3D project was with Dr. Alifa Hack. And so I was tasked with figuring out the 3D overlap between fisheries and species. And so this is where typical 2D tooling ran out. We have R packages like SF and Terra for 2D analyses, but nothing straightforward for depth-aware operations. And so to show this, we have a 3D recipe. So the first ingredient is the outline of the species range. So for example, the species range from the IUCN Red List. The second ingredient are the depth minimum and maximum values. And then finally, the bathymetry of the study area. And so putting this all together, we can create this 3D raster stack representation of the species range. And so I took those 2D shapes and rasterized them at a set of standard depths. And in the brown, actually I'll show you the next slide here. So this 3D visualization here might show it a little bit better, but each stack there is one raster. And it also takes into account the bathymetry so that the rasters are only present within the water column. And so we repeat the same thing for the fisheries instead. So we take the outline of the fishing ground, take the depth minimum and maximum of the gear types and the bathymetry, and we can also turn that into a raster stack representation of the volume of space that those fisheries operate at. And then we can then overlap those 3D ranges with one another to get not just an area of overlap between species and fisheries, but a volume overlap between the two. And so going back to the Bangladesh case study, and so with this toolkit, we can then compute the volume overlap between each species range and gear type and visualize that data as a cross-section of cell depths. And so the figure on the left here shows the cells that overlap in 2D. Imagine looking at each of those cells from the side view. And so we have not only the area overlap from the map on the right, but you can also see that there's a difference in overlap on the left between the fisheries depths and the species depths that isn't revealed when we just look at it in 2D. And so if we were to take that workflow and represent it in the code from my package, we first have a function for rasterizing or creating that raster stack from the ranges. And then we have the next function here for calculating the volume of overlap between the stacks. And so what we just walked through visually, showing it in code, it looks something like this. The next project I worked on was working with some World Ocean Atlas data. And so this is a map of the world's sea surface temperature, which I'm sure many of you have seen. And we often use this to describe the habitat conditions that sharks and rays exist in. Again, the problem, this only shows the variables at the sea surface rather than the full depth that sharks and rays occupy. And so for this next project, I extracted abiotic factors like temperature and dissolved oxygen for the full 3D range of every shark and ray in the IUCN Red List with available range and depth data. And so we got those values for 57 standard depths from 0 to 1,500 meters. I have the example of the great white shark on the screen here to show the kind of range of those temperatures across its full depth range in addition to its area. And so showing this as the code, or showing this as the functions in my code here. So we have one utility for downloading and loading the World Ocean Atlas data. And then we also have another function here for essentially cropping that environmental raster by a species range, not just by area, but also by depth. And so that gives us this end result here. And so the next and last project I've worked on most recently is working with Global Fishing Watch data. So they have a apparent fishing effort raster that is global and gear attributed and quite high resolution. But again, the problem is that it's flat. All that fisheries effort is represented in just 2D. So my package gives you a way to extend that 2D raster data into 3D. So here I have a figure with the benthic fishery types. So for example, bottom trawling clamped to the bathymetry of the area around Japan and visualized in 3D. And so this workflow in code, we take the Global Fishing Watch API and take that tabular data. We can convert it into a spatial raster. And then we have a function for taking the benthic fisheries effort and bounding it to the seafloor, and also taking the pelagic fisheries at their respective depth ranges. And so while there are some limitations with the publicly available Global Fishing Watch data, so for example, Global Fishing Watch labels both midwater and bottom trawlers as simply trawlers. And in 2D, that doesn't matter so much. But in 3D, they obviously exist in completely different parts of the water column. But the point that I want to land here is that this package is about the infrastructure of the workflow, not a finished claim about any particular fishery. This workflow is separate from the quality of the data that is going in. As Global Fishing Watch's data improves, that new data can drop in straight into the workflow without removing or rewriting downstream code. And so absorb the improvements in data as it comes. So the approach I took with the development of this package is to try to think like a software developer. Some of the core tools that I used include open sourcing the package, using Git, writing functions with clear inputs and outputs, and writing tests that check the functions against known inputs and outputs. This is more work than writing a typical R script, but it really helps with reproducibility, collaboration, and for the next thing I want to talk about, AI. Scary. So to say it bluntly, if you want to use AI, you better have these tools locked in. They're the essential tools for keeping AI from taking over. But yeah, basically using AI responsibly and increasing our accountability with it. So to be clear, I did use Claude Code for the development of this package, but I did not use it for the methodology or interpreting of the results. And so in terms of future directions for this work, I would be really interested in creating species distribution models in 3D, mapping some 3D movement from shark tagging data, looking at spatial protections and management, and integrating some additional data sets like the Copernicus marine data. So I want to thank my collaborators over the years. It's been wonderful to work with all of you. And you can access the code for this package at the QR code there. And then one quick note before we open it up. Alongside this work, I'm actually freelancing as a developer and researcher. So I'm looking for more projects. So if anything I've shown you connects with your work, please come find me after the talk or drop me an email. I'd love to hear what you're working on. Thank you.
Thank you so much, Jay. We have no more time for questions, but thank you. And can I have a round of applause for all the presenters of this session? This was amazing.